Hi everyone, I'm Hitesh. Today I'm going to talk on topic on video compression by using AI-based approach, and my topic is on optimal video compression using pixel shift tracking method. So before getting into the topic, I would like to give a quick introduction about myself. I'm Hitesh. I've been working as a senior machine learning engineer for Expedia Group. I have over 7 years of experience in the field of machine learning and AI. I have worked in several industries like insurtech, fintech, and now I'm working in travel industries. I did my master's in machine learning and statistics, and from that, it's been quite a journey in the field of AI. And we recently worked on this research idea on video compression, and that's what I'm going to talk about today. Let's get into the topic. So, just to give a quick introduction, in today's world, videos traffic is comprised on almost 85% of the internet's traffic. From social media alone, we get around 10 petabytes of data every day gets processed and stored into the cloud environments. So there are around 20 different video compression methods which has been used and being used in the industry. And most of them are a rule-based algorithm approaches. In recent times, there has been a lot of research happening in the machine learning field on computation side on trying to use AI-based approach to do compressions of the videos. And the main purpose of the research is happening in ML space for video compression is that using ML, it can be used across a diverse video format, irrespective of what format we are trying to use. And also it can be tapped across any ML framework, irrespective of trying to just be possible in one framework. It is framework independent and also diverse in video formats. We are proposing another approach over here, and so that's what I'm going to talk about. So before getting into more detail about our idea, I would just like to give some quick idea of how the video compressions, what type of video compressions are done today, and then we can get into the topic of our approach on the pixel shift tracking method. So in the current traditional compression algorithm, these are the formats we have been using, which is the H264, H265, AV1, VP8. All these things could be, for some, it could be familiar or unfamiliar, but all of these traditional algorithm methods are being used to store all these MPEG files, MP4s, MP5s for audios, and MPEG files for videos. And the algorithm which is being used at the backend for the compressions of the videos or these algorithms basically. So there are basically two types of compressions. One is lossless compression and the lossy compressions. So lossy compressions are the mostly used format where when we try to compress data or when I try to write and store a data in terms of video, we do see some decrease in the quality of the video, and that's the lossy compressions. And there's lossless compression, which is more of the high definition videos which we talk about. But most of the videos which you write or upload to any social media or any cloud storages, all of them are being compressed, and that's a lossy approach. And the approach which we are going to talk about today is also a lossy based approach. Lossies are not basically something where the data will be lost. Rather, it's just the decrease in the quality of the video, but from a normal human standpoint, a human viewpoint, you wouldn't see a lot of data losses. But granularly, if you try to see that, there will be a lot of data losses happening. But that's the only thing which we lose. But eventually we try to compress these videos and store in a more optimal way. And so that's the lossy approach. And one of the approaches which we are proposing today is also a lossy based approach. And today in the AI machine learning space, these are some of the areas the researchers are happening on the video compressions, which is tapped by the retrieval encoders, VAE, which is the variant auto encoders, and deep contextual network. So our idea is also based on a deep contextual network over here. And that's what I'm going to talk about today for our approach, which is the pixel point tracking approach to the video compression. Yeah, so this is a proposed method. So the way we have approached this problem is basically trying to avoid the redundant pixels in a video while storing. So just to give a quick example, so videos are basically comprised of frames. For any given video, let's say even a high second video, there will be at least 20 to 30 frames, which we have, which are basically the images. So when we see as a video, we saw a lot of things moving here and there as a video, but if you see as a frame, or frame by frame, image by image, we basically see there's a lot of redundancy happening from one frame to another frame. which is basically restoring the same pixels or the same data from one frame to another frame. And that's what we are trying to avoid by not storing those redundant frames from one frame to another frame on all the subsequent frames, and reduce all those unwanted data. And we're trying to optimize the storage when we try to store using machine learning based approach. So the way we are approaching, way we are trying to find this redundant pixel is basically trying to track the pixels. So for example, when a video has been taken, so that you know that a video moves in a particular directions, right? So it can move from left to right or top to bottom, or it can move from left to top or right to top or up top to bottom. The video can move any ways. So based on the movement of the videos, using their coordinates, we're trying to understand how far it has moved from a point A to point B. Based on that, we know how far the new pixels we are going to get in the next frame, and what are the other redundant pixels we are going to get in the next frame from the first frame. And we're trying to nullify those and trying to put a black spot on those. By doing so, we eventually ready the size of a frame or size of an image in a video. So there are two different approaches. One is a single point trajectory method and the multi-point trajectory method. So the single point trajectory method is basically trying to find an arbitrary point and we are trying to track it. A multi-point is basically on trying to use multiple points and trying to track the video movement or the frames movement. So I'll get into details now, starting with the single point trajectory. So for a single point trajectory, what we basically do is we try to find an arbitrary point in a video in a starting first frame. And from there, we try to basically track that point from one frame to another frame. And this is where we are using a deep learning computer vision approach. We're using a concept called persistent independent particles, which is called PIPs. It's a research paper written by another researchers. And we made use of that over here and to optimize that PIPs concept in a way. And we are trying to achieve the video compression over here. And that's our approach basically. So we basically try to use a single point trajectory over here, which is basically trying to find an arbitrary point in the first frame of a video. And from that, we basically try to track where the particular object or a point or a pixel is moving from one frame to another frame to the subsequent frame. Based on that, we know how many coordinates it's moving. Based on that, we try to see how many new pixels we are going to get. And that's what we install. We try to avoid the rest. So the single point trajectory basically works only in places where the objects are static and the video is moving. So there are three different ways a video can be seen. So one is where the objects are static, where the video is moving or the camera is moving, or the camera is static, but the objects are moving. Or it could be the both. The cameras and object could be moving at the same time in a video. So there are three different approaches. The single point tracking can solve only in scenarios where the objects are static, but the camera is moving. But multi-point trajectory can do it way better by trying to have multiple pixel point tracking trajectories, and based on we can try to get an average movement of it, and we try to avoid the rhythm of pixels. So before getting into multi-point trajectory, I'll just show you a quick example of how this tracking looks like. You can see here in this picture, there is a dog running. This is a video where we are trying to track the nose of the dog. So the idea is not to track an object here. The idea is basically to track a particular pixel. And based upon the pixel movement, we can identify what is the redundant or the non-redundant part of it. As I mentioned, this single point trajectory is achievable through through a method where the objects are static, where the camera is moving. So that's what the single point tracking looks like. When we try to track it using machine learning, then we're trying to use the frames to see where the objects is moving. The pixel point is moving. So to talk about the multi-point trajectory, as I mentioned, so multi-point trajectory basically works when where you try to put the pixel points, the trajectory points in multiple places in like a grid format, in a 2D grid format. And by doing so, now what it does is in a given frame, let's say we have an 8x8 frame where you put 64 points or 64 trajectory points, which can track all the 64 positions within a midpoint of the every small grid positions within the 8x8 pixel image. So by 8x8 image size. So by doing so, what happens is it can also track object movement. It can also track the camera movements. And by calibrating all of those, we can try to find what is the only redundant part, what are the non-redundant part which we can expect in the next frame compared to the first frame. And this can mostly work in a very advanced approaches where the videos is very complex. And that's where the multi-point trajectory would eventually be helpful. To just give a quick visual of how the multi-point trajectory would like will look like is from the previous video we saw that there was a dog and the dog was moving and we were just pointing one trajectory. And I can go back here. So you can see here it's just tracking one trajectory. And this trajectory looks like it's going like it looks like some kind of leap, right? So that's why it's moving. But in this case, in this video, we can see that the dog, the object, as well as the video, both are moving. So a single point trajectory would not effectively can say how the pixels are moving. But by using a multi-point trajectory, you can see here actually how the entire video from one frame to another frame, or at least this is like let's say it's a 2-second video, might be we have 4 to 5 frames in this. We can see from frame 1 to frame 5 how far it has been shifted. So this can give like an overview of how the pixels are moving at different positions. And based on that, every single positions, we can see what are the pixels we need to store, what are the coordinates we need to store, what are the position coordinates we can avoid storing, and we can retrieve it from the previous frame. And that's what we are trying to do over it. So let's get into the steps on how we have achieved it. So for the compression step, just to give a quick note, in this approach, we are trying to prove that this is possible to pixel point tracking by using single trajectory method. So we have used that as a proof of concept over here to display it and show that this is possible. And so as a step 1, for using single point trajectory method, we arbitrarily choose a point in a video. So we are using a video. We used a video where the objects are standing, but the camera is moving, the video is moving. Basically in the video, the camera is moving. Sorry. We use like let's say a midpoint in the frame and we are tracking that point over here. So we choose an arbitrary point for the pitch to track, the present independent particles model to track. And it basically processes 8 frames at a time. So to improve that accuracy, we are trying to use 1 frame at a time to predict where the pixels are moving. So where the point is moving from one frame from first frame to second frame for the given pixel point. So we place a random point, arbitrary point in the first frame, and then we try to track the frame from frame by frame, one frame to another frame, while we are trying to track. So let's say we were at a point in frame 1, and eventually when we try to move from frame 1 to frame 2, let's say it moved 4 coordinates to the right, we know that there is going to be a width of 4 pixels, a width of 4 size pixels going to come inside. And I know the rest of that part on the left side of the first frame is going to be redundant and should be available same pixels in the second frame. So that's what we're going to nullify and delete that and store only the non-redundant pixels. And that's what the compression part does for one frame to the second frame. And similarly from second frame to the third frame and to so on, that's how we try to compress these. To just give a quick idea of how that looks like, you can see here in the frame 1. In the frame 1, we can see that. So in the frame 1, we can see that over here that this is the complete image. And in the frame 2, what's happening is it has moved like few pixels to the right. So when we are trying to do the compression, the second frame won't look like how we see in the second picture over here. Rather, it would look like the third picture in the image, where it basically nullifies all of the redundant pixels and it stores only the non-redundant pixel in the storage for the second frame. Similarly, we do it from the third frame, fourth frame, and so on. And by doing so, we try, as we're putting a black value of 0 in terms of pixel to all the redundant part, we reduce the size during the compression. Well, this is how the compression part works. And now I'll get into how the decompression part works. So the decompression part is an interesting one. It's a very intuitive approach. So what we have done is, in the process of this compressions, the first frame will always remain intact. That basically means like it will be whatever it is, the first frame, it remains the same. Because for the first frame, there is nothing called redundant pixel. That's the first frame. So first frame always stores the entire data without nullifying any of the data points in the data points, which are so-called the pixels. So now what happens during the decompression step over here is, so during the compression, we know that from frame 1 to frame 2, it moved 4 coordinates to the right on the x-axis. So what we basically do is that's the only new width which we're looking for the second frame, and that's what we store from the second frame, and we nullify the rest. So those nullified positions are stored as an array on collecting those coordinates positions alone, which is basically the x-axis and the y-axis points on basically, let's say, like a rectangle. So it takes 4 coordinate points and we store it for every frame on what has to be recomposed when we try to do the decompressions. So basically, when we do the compression, we stored all the frames by storing only the non-redundant pixels, and then we also store a separate array, which basically holds the coordinates of the redundant positions, which can be obtained from the previous frame. So how that basically would work is, if you see here in the first image, the data retrieval frame, right? So this is the first frame. From the first frame to second frame, if you see the second, wherever that's in shade, those are the non-redundant pixels. Wherever it's black is the redundant part. So once it's basically showing us is over here, from the first frame to the second frame when it moved, the point has moved like this, the camera has moved like this. So it had moved from this position to move like little bit tilted towards downside. So those are the new pixels just coming inside the second frame. So that's what we're storing, and we remove the rest of it and store it. So to reconstruct those second frame with all the pixels, I mean, with all the remaining redundant part, to make it as a video at the end, what we do is we take the redundant part from the first pixel, because first frame, we know the first frame is completely intact where it has all their pixels. From the first frame, we take the redundant part, and which is basically the inverse position of the second frame's redundant position. So the second frame's redundant coordinates would be the reverse of the first frame's coordinates positions. So because that's why the video is moved like this. So we try to take the redundant part of the pixels, try to reconstruct the second frame. So second frame will be reconstructed now. Similarly, we do that for the subsequent frames, for frame 2, frame 3, and until the frame. By doing so, we do the decompression, we bring back everything in. So that's how we are approaching this, and that's how we do the decompression. And this is basically what we have done the POC on the single point tracking. So in terms of the results over here, yeah. So what we were able to achieve is the compression we try to do is like a 15 times per frame. So that basically means we are taking like a 15 milliseconds times per. It takes 15 milliseconds to do the compression per frame, and resulting in size of 36 kilobytes. That's the average size of per frame which we are trying to compress over here, and it takes around 15 milliseconds per frame. So like say we have 1,000 frames, it would be basically 15,000 milliseconds. So similarly for decompression, it's taking around 50 milliseconds over here. And as we are decompressing, we need to reconstruct the frames, and that's adds some extra time per frame. And it reconstructs back the images, with each frames looks like around 238 kilobytes over here. And that's what it has been used. There could be a question of why the compression and decompression takes the 15 milliseconds and 50 milliseconds. Is basically the model, when we are trying to do the compression, the model has to do the predictions as well. So it has to do the predictions on where this pixel is moving from one point to the next, from one frame to the next frame. So the model takes some few milliseconds, and also we have a built-in algorithm on top of it, which actually use those coordinates to nullify and store those redundant pixels into an array, pixel coordinates into an array, and this just store the non-redundant pixels from their subsequent frames and so on. So that's why it takes 15 milliseconds and 50 milliseconds per frame. And eventually for like a 1 minute video, it takes around, currently it's taking around close to a minute. For 2 minutes video, it takes close to a minute to do the compressions and store it. And also the decompression takes pretty much close to 2 minutes to do that. So it's quite kind of little slow. The reason is we are trying to do the prediction per frame, but we can also try to do the prediction per 8 frames. Let's say we have 64 frames in a video, and we can just do it in 8 iterations by trying to predict each 8 frames and trying to store it. But eventually what happened was the loss was more when we tried to do eight frames. The prediction was dropping, and eventually the data loss was increasing. We had to use per single frame at a time, so that the accuracy is really good and the loss is less, so that we can try to save a lot of data and reduce the data losses, and to try to benchmark it against the existing traditional algorithm methods. And you can see that in this graph, right? So as we try to do the compression per 8 frames or per 7 frames or per 6 frames, you can see that the reduction in the size is pretty good. When we try to do per 8 frames, we are able to reduce the compression. We will reduce the size or like 82%. but 82% compared to the one frame using one frame for predictions. By doing so, we can reduce a lot of the size, and also it can be faster. But the problem is the reason that's able to reduce in size is because increasing number of frames to do the time to do the prediction also add a lot of losses to the data. That's why we see the reduction in the total size when we do the compression. And you can see the right hand side graph where as we increase number of frames to use at a time to do the prediction for all of the pixel movements. So if we use like 8 frames, it tries to predict the arbitrary point on say where it is moving in the first 8 pixels. So the accuracy is going down because of that. The way the algorithm is working to do the reduction of the redundant pixels, it also does the wrong thing because it eventually end up having a lot of data losses. And because of that, we can see that the compression percentage is pretty high when we try to use number of frames, but also the loss is also high. So in the right hand side graph, you can see that the loss is going pretty high when we try to increase the prediction per 8 frames at a time, per 8 frames at a time. So if we try to do one frame, you can see the loss is very less, close to 4%. Whereas if we try to use 8 frames using pips plus, it's around 7% of data loss, which is pretty high. Eventually, you can see that the quality will be not very good actually. So then you can see this. The reason for you to see there are two lines over here. One is Pips and Pips plus plus. There are two different models. One is Pips, which is initial version, and Pips plus is the version 2 of it, which does some better predictions on tracking the trajectories of the pixel point, which we're using to track the moment of the video to avoid the redundant part. So and that's why we try to use both the models to evaluate the performance. And eventually, in both the models, using single frame at a time to do the prediction does better because single frame instance like using 2 frames at a time. So it can predict from frame number 1 to frame number 2 on how where the pixel has been actually shifted. And that's what the performance graph looks like. And we were able to achieve a better performance by using single frame predictions at a time in the model. So the loss was very much close to 4%. So we were able to retain 96% of the data. And the loss is basically not like a visible loss where you will see black dots here and there. No, it's not like visibly you might still see the video working fine. But in terms of the quality, there's a 4% reduction quality, but still we were able to do the compression way better by reducing the size of the storage by 80%. That's something really great, around 84% with just 4% loss in data. That's a good cut over there. And this is more of like an initial approach of using redundant concept over here to do the storage using an ML based approach. So just further approaches and ideas for viewers who are listening to this, we can try to use this multiple point trajectories. And that's what we are trying to work on for our next research paper, where we're trying to improve this performance for more complex videos, where we try to put the trajectories on multiple directions. And another approach is basically the object detection masking. This is basically works in places where, let's say, in a given frame, there are a human or dog or any kind of object. We can mask all those objects and understand their pixels in a very low way. Like you can put a mask on top of it, and you can try to identify the same mask or the same person's second pixel, and can eventually try to avoid those redundant pixels in the subsequent frames by masking those objects. And then another approach is similarity search. Similarity search metrics is basically can be used where if you see any similar pixels which are already available in the previous frame compared to the new frame at every pixel level, using similarity search metrics, using any kind of cosine similarities or any kind of dot product similarities, we can try to see how close these pixels are. And we can try not to store those pixels in the subsequent frames so that we can reuse it and map and reuse these pixels in all those places when we try to do the decompression. So these are some of the approaches which you can try. Open to anyone can give a try on this and try to see if we can come up with a better approaches or better solutions. Yeah, these are the future approaches, and I'm hoping machine learning and these AI models not only uses a lot of data to train themselves, but also I hope that gives us scope for us to use AI to also reduce data storage, because a lot of data storage in today's world is being used to train these machine learning models. In return, I hope these machine learning models can also contribute in a way where it can store things in an optimal way and reduce cost for us. So that's a good takeaway out of this talk, that AI not only uses a lot of data, but it can also help us optimize these usage of data or storage of the data. And this is one such approach which we try. And That's all. And these are some of the references. That's the research paper which you can look into, repos there. And these are some of the other references which we looked into to inspire from them and to work on these optimization approaches using deep learning methods, especially use the deep or convolutional neural network methods over here. And that's what this video is all about. And I hope you all enjoyed my talk. And feel free to reach out to me if you have any questions. Would love to answer. And thank you.